Truscott with SUNY Brockport, and I'll let you take it away, but talking about thiamine deficiency, so have at it.
All right. Thank you. Good morning, everybody. My name is Jonathan Truscott. I'm a graduate student in Dr. Inchard's lab at SUNY Brockport, and today I'll be presenting some preliminary findings of my thesis research, a part of my thesis research, which focuses on evaluating thiamine deficiency in lake whitefish as a potential cause of their recruitment failure here in the Great Lakes. So to begin, I just wanted to start off with a brief overview of whitefish. Lake whitefish are an ecologically, economically, and culturally important species to the Great Lakes region. They're a keystone species in the Great Lakes aquatic food webs, linking both nearshore and offshore waters, and greatly contributing to the nutrient partitioning between both benthic and pelagic zones. Today they make up the highest proportion of our commercially harvested species here in the Great Lakes, with most of our annual harvests coming from Lakes Michigan and Huron. And finally, they hold tremendous cultural value to the indigenous communities throughout this region, and have continued to do so for thousands of years. Over the last 20 years, however, we've begun to see substantial declines in lake whitefish populations, especially throughout the lower four Great Lakes. And these declines have largely been attributed to these benthic regime shifts following the invasion of your Dreissenen mussels, so your zebra and quagga mussels. So as such, these declines create extensive concern over the status of the commercial fisheries for lake whitefish, as well as their populations as a whole in each of the Great Lakes. Moving on into the diets of lake whitefish, historically they were composed of prey species like Diperia and Mysis, which were high in caloric value, as well as the fatty acids 25N3 and 22,6N3. Now, since their invasion in the 1990s, Dreissenen mussels have acted essentially as ecosystem engineers, redirecting nutrients to nearshore waters and reducing offshore nutrients for prey species like Diperia and Mysis. As such, subsequent declines in Diperia populations have thus shifted lake whitefish diets towards more abundant, less nutritionally inferior prey, or nutritionally inferior prey items, for example, such as your Dreissenen mussels. And this creates concern because Dreissenen mussels are very high in thiaminase 1 activity, so one of the roles of thiaminase 1 being the breakdown of thiamine. As such, this creates concern that lake whitefish may potentially be limited in their overall thiamine intake required for physiological functioning and overall survival of both juvenile, adult, as well as lake whitefish embryos. And so because they're beginning to consume more and more mussels and other nutritionally inferior prey items, this begs the question, are lake whitefish affected by thiamine deficiency? Now, thiamine deficiency complex, or TDC, is a major physiological stressor affecting the recruitment of several Great Lakes salmonid species. For example, one of the most well-known ones is our lake trout here in the Great Lakes. Essentially, a lack of maternal dietary thiamine intake it essentially means less thiamine reserves are transferred to the eggs, leading to poor development and early life stage mortality of the embryos. There are two proposed mechanisms for thiamine deficiency complex in Great Lakes salmonids, those being thiaminase 1 activity that I had mentioned previously, and the second being the excessive consumption of lipids leading to the deposition of long-chain fatty acids in the tissues of the fish, creating oxidative stress and depleting the necessary thiamine reserves. So therefore, the consumption of nutritionally inferior prey may induce thiamine deficiency within lake whitefish and overall affecting the natural recruitment of the species. Therefore, it's an imperative that we evaluate the diets of lake whitefish to determine the presence or absence of thiamine deficiency complex within this species. And this brings me to the goal of my project, which is to evaluate thiamine deficiency in lake whitefish as a potential cause of the recruitment failure. For my project, I have made 4 main objectives. However, for today's sake, I'll be focusing on Objective 1, to compare lake whitefish egg thiamine concentrations from multiple sites across the Great Lakes region. And Objective 3, to evaluate the diets of adult female lake whitefish through analyses of stomach contents, fatty acids, and stable isotopes. For today's talk in particular, I'll be focusing solely on the fatty acid component of both lake whitefish and their diets. So moving on to our sample collection, in the fall of 2024, we targeted 30 adult females from multiple sites across the Great Lakes region. In 2024, we had a total of 16 sampling sites and collected over 300 whitefish for this project. As we all know, fisheries is never an exact, we never get our exact sample size that we want, so some sites had more than others that we were hoping for. From each of these fish, we collected eggs, dorsal muscle tissue, belly flap tissue, as well as stomachs. And also from each of the Great Lakes, we collected prey samples. So we collected 30 individuals per prey fish species and 200 to 300 individuals per invertebrate species like Mysis, Dreissena mussels, and so forth. For prey samples less than 5 grams, or for most invertebrate samples in our lab, we made composite samples to run our analyses. So thiamine was extracted from the eggs of lake whitefish as well as homogeneous prey samples, but today it's only going to be focusing on the extraction of thiamine from the eggs of lake whitefish. The vitamins-free thiamine, thiamine monophosphate, and thiamine pyrophosphate were quantified using high-performance liquid chromatography, and these were then summed to express the total thiamine concentrations in nanomoles per gram. Lipids were extracted from the belly flap tissues of lake whitefish as well as homogeneous prey samples. These fatty acids were then transmethylated and analyzed using gas chromatography, mass spectrometry. So why do I use fatty acid analysis in particular? Well, fatty acids are critical for both development and reproduction, but they're also important biomarkers of the dietary history of fishes, essentially following the principle of you are what you eat. So as we jump into some of the results from our 2024 sampling, using these approaches, we can look at the patterns that have emerged from both lake whitefish egg thiamine concentrations as well as their diets. So taking a look at the egg thiamine concentrations from 2024, we can see that there are there is spatial variations observed both across the sites as well as among each of the Great Lakes. In particular, we can see that Lake Michigan had the widest variation in their egg thiamine concentrations, and this may be due just because Lake Michigan had far more sites sampled than the other Great Lakes as a whole. For example, Lake Erie only had one sampling site in the fall of 2024. We can also see that there are wide variation among the females within each location. Again, I'm pointing to Lake Michigan, mostly because it's the most diverse in terms of its egg thiamine concentrations. Mean egg thiamine concentrations overall were relatively high across all sites, averaging around 9 nanomoles per gram or higher. It is important to note, though, however, that I am pointing out here is that the lethal threshold inducing 50% mortality, or the LC50, for this species is currently unknown. So as part of our research, we are investigating what that LC50 for lake whitefish may be, and I'll jump into that a little bit later on in this presentation. Now, as moving on into our fatty acid analyses for the lake whitefish belly flap tissues as well as homogeneous prey samples, I conducted principal component analyses for all these samples using primer. And what we can see is distinct groupings of belly flap fatty acid signatures among the lake whitefish from different locations. For this project, or for today's focus, I focused on Lake Superior, Michigan, and Ontario, mostly because I had both prey samples as well as lake whitefish collected from those locations. And what we can see is that Lake Ontario sites were very rich in the fatty acids 18, 1, and 9, whereas most of the Lake Superior and Lake Michigan sites in the lower left corner of the PCA were more rich in the fatty acids 16, 0, and 22, 6, and 3. There is a group of Lake Michigan sites, or Lake Michigan whitefish, that were also rich in the fatty acids 16, 1, and 7, and 25, and 3. And so essentially what this tells us is that the differences that we're observing among these lake whitefish samples may either be due to the consumption of different prey samples, or that the prey samples are different among locations in terms of their fatty acid signatures. Breaking it down further by the sampling sites, we can see similarities and differences in the fatty acid signatures of Lake Whitefish. And then in particular, what we can see is that that group of Lake Michigan sites was all the Fox River whitefish. So the Fox River is very, very rich in the fatty acids 25 and 3 and 16, 1 and 7. Lake Ontario samples were mostly composed of that 18, 1 and 9. And then most of the other Lake Superior and Lake Michigan sites were rich in 16-0 and 22-6 and 3. It is worth noting that there are some Lake Michigan sites, Little Traverse Bay and Grand Traverse Bay in particular, that share similar fatty acid signatures to those of the Lake Whitefish from Lake Ontario, and therefore suggesting that they may be consuming similar prey items to those fish compared to the other Lake Michigan sites. I also conducted a principal PCA of the prey samples as well, and from here we can see distinct groupings among our prey samples. One of the things I think is worth noting is that there are also differences between each of the species based from the spatial variation. So our Lake Michigan dry-sided mussels, for example, were higher in the fatty acid 16-0 compared to our Lake Ontario samples, which were in 16, 1 and 7. So breaking it down further, we're going to go into each lake as a whole. Looking at Lake Ontario prey samples, we can see distinct groupings between our fatty acid signatures among our prey. The mysis in particular were rich in the fatty acid 18, 1 and 9, dry-sided mussels in 16-0 and 16, 1 and 7, and our round goby in 18, 1 and 9 and 22, 6 and 3. When we compare this to the fatty acid signatures of the belly flaps of Lake Ontario whitefish were not significantly different. You know, this PCA is very messy looking. There's no distinct groupings between the two sampling sites from Lake Ontario. And so essentially what this may be suggesting is that the fish from both Bay of Quinte and Point Peter may be consuming a combination of all three species represented here. Similar to Lake Ontario prey, Lake Michigan prey samples show distinct groupings between their fatty acid signatures. Mysis in 18, 1 and 9 and 22, 5 and 3. Dry-sided mussels in 16-0 and round goby in 16, 1 and 7 and 22, 6 and 3. Again, comparing this to their fatty acid signatures of whitefish samples from Lake Michigan, that Fox River sample that I mentioned was rich in the fatty acids 25 and 3 and 16, 1 and 7. More closely aligns with the fatty acid signatures of the round goby, suggesting that Fox River whitefish may be consuming round goby as their predominant prey source. Grand Traverse Bay and Little Traverse Bay were more rich in the fatty acid 18, 1 and 9, suggesting more composition of mysis in their diets. And finally, all the remaining East Coast Lake Michigan sites, Arcadia Reef, Ludington, Muskegon, and Saugatuck, within those two other fatty acids, 16-0, 22, 6, and 3, but primarily 16-0, suggesting a greater consumption of those dry-sided mussels. And finally, breaking it down for Lake Superior, we can see that mysis and sculpin, zooplankton, as well as rainbow smelt, show distinct groupings from each other. Mysis and sculpin were rich in fatty acids 16, 1 and 7, 18, 1 and 9, and 22, 6 and 3, or 25 and 3, sorry. Rainbow smelt were rich in fatty acids 22, 6 and 3, and zooplankton in that 16-0. Now the Lake Whitefish fatty acid signatures for Lake Superior were a little bit variable, but primarily what we can see is that Gull Island whitefish, which is closer to the Duluth area of Lake Superior, those fatty acid signatures more closely align with diets composed of mainly smelt, so juveniles, or young a year to juvenile smelt. And finally, your Birch Point and St. Mary's River sites, those whitefish showed consumptions of 18, 1 and 9, or 16, 1 and 7, 18, 1 and 9, and 16-0, suggesting the prey composition there may be mostly composed of mysis, potentially some sculpin, as well as zooplankton. And so essentially what all of this entails is that lake whitefish differ spatially in their diets, and therefore continued monitoring of both lake whitefish populations and their diets is critical to understanding how changing prey assemblages may be affecting the maternal provisioning and recruitment in lake whitefish. So moving on, the next steps for this project, future dietary analyses like stomach content analysis and stable isotope analysis will be used to complement the results of our fatty acid analyses. Stable isotope analysis is currently underway with our collaborators at the University of Windsor on most of our prey samples, and eventually we'll be sending them our stable isotope samples for the lake whitefish. Eventually these will be used to correlate stomach content, fatty acid, and stable isotope analyses to those egg thiamine concentrations to assess the relative presence or absence of thiamine deficiency in lake whitefish. We'll also be conducting some thiaminase activity analysis of the prey species. That's currently being conducted by our collaborators at the USGS Columbia Environmental Research Center. And finally, as I mentioned before, to assess that LC50 for lake whitefish, we are currently rearing lake whitefish in one of our hatchery tanks at SUNY Brockport. And again, these fish will be monitored from when they hatch to the swarm up stage and see if there's any signs of thiamine deficiency. And with that, there's simply not enough time to thank each and every individual that's contributed to this, to my project so far. However, I'd like to say a big thank you to my advisor, Dr. Richard, as well as my advisory committee, Dr. Michael Chislock from SUNY Brockport, Jason Smith from the Bay Mills Indian community, and Dr. Timothy Johnson from the Ontario Ministry of Natural Resources and Forestry for all of their support and guidance throughout this project. To the many tribal, state, federal, provincial, and university collaborators involved in this project, especially for their assistance with all the sampling, sample collections in the fall of 2024 as well as 2025. To the graduate and undergraduate students from SUNY Brockport for their assistance with laboratory analyses. And then finally to the Great Lakes Fishery Trust and SUNY Brockport's Distinguished Professor Award for their financial support. So I just want to say thank you all for coming out today, and with that I'll take any questions.